In this lesson, we're going to discuss another option we have on the spectrometer, on the setup of the spectrometer. Over here, on the top, okay, let's put the spectrometer like this. We have this knob over here. I can turn this knob left and right, clockwise and anti-clockwise. Generally, when we ship the instrument, you will read here there is a 2, for example, 2x or another number, and so this will be the correspondence position where you will find your system when you receive it. So in case accidentally you turn this knob, you know that you have to follow this link over here. 2x correspond to the 2x over here on the knob. Okay, so in this case, okay, we go back on the table. I can turn the knob until it is 2x corresponding to 2x. Okay, so in the previous lessons, we had this position 2x and 2x. What is this knob? This knob change the width of the slit of the spectrometer. The slit of the spectrometer basically is this aperture that we have on the spectrometer, and the idea is that we can have it very close. We are talking about a fraction of a millimeter or the maximum open. So why we have this possibility to change the aperture, the slit of the spectrometer? Basically, the idea is we have to compromise. So, for example, if we turn it clockwise, basically we are closing the slit. So what happens when we close the slit the maximum? The resolution of the spectrometer is better. So basically we have a better spectrum in terms of resolution. So one peak, instead of being like this, for example, it will be very thin. So, for example, that position 1000 nanometer will be very thin. So this is useful because, of course, we can distinguish better the spectra. So the idea is why we don't keep the slit always as close as possible, very little, very narrow. The problem is that when the slit is very close, we have less light going into the spectrometer. So what happens is that the signal is low, is small. So in this approach, make overall the peaks less visible. Okay, so the idea is when you are familiar now with Raman spectroscopy, you can basically play with the slits in order to make the spectrum more visible, the peaks more visible. We are starting to discuss a specific case. So this is this method of this changing the slit, make it very narrow, so the smaller as possible. It's useful in particular with very fluorescent pigments, like the organic pigments, and in particular we are going to see naphthol red. So in this case, basically we have a lot of signal because the pigment is fluorescent itself. So we have a lot of signal. So if we close the maximum, the slit, it doesn't make any difference. Still, we're gonna have plenty of signal. Okay, so let's go directly to do the experiment. We are going to use a pigment checker. So here we have our collection of historical pigments for testing. Okay, there we are. And so we can take out the pigment checker. Okay, so over here is naphthol red. So we want to keep it in position. So I'm using this this lift, lab lift, and we are going to put the pigment checker in front of the Raman. I'm going to use this magnet just to hold the pigment checker in a position, and I'm getting closer. Okay. Over here we're gonna use the camera just to check that we are facing the right pigment. Okay, there we are. Okay, so now we are on the camera. There is plenty of light. I can turn on my lights over here. Try to do a preliminary focusing. Okay, out of focus, on focus. Okay, there we are. Okay, maybe too close, a little bit less. Okay, there. At this point, we can turn on the camera, off the camera. We don't need it, and here we are. So we can turn on the laser. Okay, so we have the laser on. We can do a little bit of testing, like moving a little bit the camera, the pigment checker, in order to see if we can get an area where we have more signal. So sometimes it's better. Okay, a little bit, 1030. So exactly, so a little bit here seems to have the better signal, it's higher. Okay, so right now the collection, you see, it's just 10 milliseconds. So definitely we need more. Let's put 100. So 100. You see the curve, it's already 15,000. So if we put like 400 milliseconds, we are close to saturation. So consider we have here 60,000, that is close to the 66,000 saturation limit, and the spectrum is almost saturated, at least here on the right. Okay, so basically right now this is the best we can do with our system to collect the spectrum of naphthol red. So the slit now is all open. So I turn basically the knob clockwise, and it's all open, the maximum. So we get a lot of signal, so our spectrum, in just 400 milliseconds, so 0.4 seconds. And over here we start in the middle of the spectrum. You see, if you see my mouse on the screen, we start to see something like peaks. So there is some specific signal, but you see the peaks are not really well defined. So this is a case where we can actually close the slit in order to get a better signal, the shape of the peaks more defined. Okay, let's see it in practice. So what I do is, first of all, I save this spectrum. So file name, we name it slit open, actually open slit, and the acquisition was 400 milliseconds, so that's the name I want to give to this spectrum. Okay, and now we do the same experiment opening the slit all the way, actually closing the slit all the way. So you see now I'm moving the slit counterclockwise, and if you look at the spectrum here on the monitor, you see that the maximum of the acquisition goes down. So now the maximum is 35,000. So I'm keeping turning, so 30,000, 25,000. Why this? Because basically, since the slit is going to be closed, the beam of the Raman signal, so we have inside, is into the spectrometer, part of this beam will be rejected, cannot go there for mechanical reason, actually, so nothing special. But what we see now is that the shape of the peaks become more clear, so we start to see better defined. Okay, I keep moving the slit, so I'm closing, closing, closing. You see again now the maximum is 11,000, and now we are, so this is basically I close almost totally, so there we are. Okay, now here I close totally the slit. So the maximum you see is just 5,000. So it's very low, this maximum. So it means we can put much longer exposure and see if we actually can raise the peaks. So for example, let's put 1 second, so 1,000. Okay, this is it, 1,000. We start to see some peaks there, but definitely we can do more, better. Let's put 5,000. Okay, you see now we have definitely much better defined peaks, so they are more sharp. Okay, so that's the goal. Okay, let's save this spectrum as it is 5 seconds. We have this acquisition, so this will be closed slit, and it was acquired with 5,000. And this 5,000 acquisition time, you see, is basically the maximum we can do, because otherwise the spectrum starts to be saturated. Remember, the maximum you can collect is 60,000 counts on the y-axis. Okay, so that's much better. Let's see what happens if we use like 2x the value here on the knob. So, which is a little bit more open. So this is basically the value that will ship your item. So it's written over here, 2 per. So I'm correspond. So I'm opening a little bit. Let's see what happens. So I started the acquisition with this 5,000 milliseconds. So now the slit is like a little bit more closed. Okay, now you see the spectrum is saturated because I used 5,000, so definitely it's too much because it's collecting much more. So let's put 1 second, see what happens. Okay, see, 1 second is still too much, so 500 milliseconds. Okay, there we are, and basically 500, the spectrum is already almost saturated, so this is it. And we see the peaks. They are not as good as before, but still, I mean, they are fine. So it's a acceptable value. So we save it. So we put 2x slit and the acquisition of 500. Okay, so in this case, so basically this is the acquisition you would do when you use the spectrometer as it is received. So my idea now is, let's see if I can get a little bit better. So I close the slit, actually I close the slit a little bit more. Okay, so for example, from a 2x I go into 1x. Okay, wait here, and the acquisition time, you see, I need to increase it because now the maximum is 25. So at least I can use 1 second, so 1000 millisecond over here, a little bit more, 1200. Even more, 400, 1400. Okay, this will be 1400 is the best. Okay, stop the acquisition and I save this one. So this will be the value of the slit is 1x slit, and the acquisition time is 1400. Okay, at this point it will be nice. Here we have the spectra, the 4 ones we collected, to compare them. So in order to do this, I use a spectrograph. So over here, let's pin to start. Okay. Okay. Remember, Spectrograph is the software I usually recommend for interpret and study the spectra we collected with ElviRa's software. Okay, so this software is much better in order to interpret data. So we start to load the spectra. We start with closed slit, so the one where the slit was totally closed. And remember, here the software, depending on the format, sometimes recognized exactly what kind of spectrum is. So if it's a Raman spectrum, if it's a reflector spectroscopy, sometimes doesn't. So in this case, we need better to give the information ourselves. So it's easy. We go here on the left for the x-axis. We put Raman shift, of course. And we can say on the right y-axis is the counts, just this number counts. We do OK. OK, and this is the spectrum. So here we have the legend for this acquisition. Let's make the legend a little bit better. So let's make bigger so we can see all. So this is the closed slit acquired with 5 seconds. So we see the peaks over there. OK, let's do the same procedure with the other. So we have open slit at 400. You see, now the software, since we already gave the information, is recognized correctly this kind of spectrum. So it says it's Raman shift counts. Okay, let's go. Okay, so let's compare this spectra now. So you see, it's the area of interest is the central one where we have the peaks. So you can tell immediately, for example, let's look at this peak, how the difference of the slit is important. When the slit is closed, we see a peak. When the slit it's not closed, it's all open, wide open, you see, we see a little bit of what I call a bump. So it's an idea that there is a peak, but the resolution is so low for this specific case that we cannot really tell it. Okay, so let's compare with the others. So then we have 1x. Okay, let's see all the spectrum together. Okay, 1x is this red one, and it's pretty nice. You see, the 1x is actually a good compromise, because what we see here, for example, let's focus on this peak in this area. Let's use this feature, the multi-cursor, okay, this one, so to indicate where we are. So this peak over here. So basically, what we see for this peak is that, well, basically, well, it's almost the same as where we have the slit totally closed. What we have is a more signal, of course, so because it's a little bit more open. Okay, so basically one X is similar, I would say, much the same as the other one, as the closed one. Let's try the other one, the 2X slit. Okay, there we are. 2X slit is over here. It's the one on the bottom. Okay, you see, in this case, the 2X slit, we miss the peak. Okay, so this is important. Okay, so basically, when I sent you the spectrometer 2X, I mean, we see the bumps, but when you are in this situation, try to close the slit and see what happens. Okay, because closing the slit will be good. Why I don't send you the spectrometer with the slit already all closed? Because there are other pigments, most of other them, it's good to have the more signal of possible. For example, you have Realgar, and we can try the other ones because they have a good signal. So it's a good compromise to have the slit a little bit more open in order to make the measurement more fast. Okay, so then it's up to you to taste the pigments and try to figure out what's good for the different situation. But now you know that you have these options. The slit option, which I recommend in particular, remember, for pigments that are very fluorescent, like these organic pigments, naphthol red, where you have a lot of signal, and inside this big fluorescence, this much signal, you have the Raman peaks in there. So in order to distinguish these peaks and these big curves, you need to have the maximum resolution possible. We present now another example about the use of the slit. In the pigment checker, we are going to check a pigment like lead tin yellow one, which has a strong signal, and we see what happens when we change the dimension of the slit. Okay, so we are going to put it in position here. Use some magnet to hold the pigment checker in position. One over here and one magnet over here. And okay, lead tin yellow, there it is. Okay, we look here at the monitor. So right now the slit, let's do the slit all the way open. Okay, so also to work with the slit, keeping it open, make, since I collect more Raman signal, also the fluorescence, I mean, it's a better way to get a lot of signal, so to check rapidly the focusing process if we are going right. So for example, now it's a 5,000, let's see the dimensions, 6,000, 7,000, 60,000 already. Okay, let's keep this distance. Okay, so this is the spectrum with the slit totally open. So we see a nice spectrum. Actually, let's save it. So I can do start this one, save. So this will be lead tin yellow, and this will be open slit. So we do save on the desktop. Okay, let's keep acquiring. So from this position, the slit is totally open. I'm closing the slit all the way. So I'm turning the knob, and you will see what happens. Basically, the main peak goes down, and the peak in the middle, this one over here, we start, so this one that does like to peak together, start to be differentiated. Okay, I'm turning the knob. Okay, so right now basically you see what happens is that I close the knob and we see a better defined peak but smaller. So what I can do is I change the scale, so now we see it better, and we save it as it is. Okay, so we go here, save. So this will be lead tin close slit. Actually, remember, what I want is to increase the exposure. So instead of this 1400, let's put more. So let's say at least 5000. So we have, basically the idea is always we want to have the maximum counts possible, 60,000. Okay, let's add auto Y scale. Okay, this is it. Let's increase it even a little more. So let's put 6,000, so it will be 6 seconds. Okay, so we are almost close to 60,000. And okay, stop, save, and this will be tin yellow, lead tin, say close slit, save, and then let's do another experiment with using the standard 2x, so the value, the intermediate value I ship the spectrometer with. So let's do an acquisition. So this should be overexposed, and then it is, no, because of course we are opening the slit. So let's put 2 seconds. Okay, actually a little bit less, so 1800. Okay, let's collect and stabilize the system. Okay, so we stop it, and this will be so we call it lead tin. 2x is the aperture, the slit dimension. Okay, so we collected the spectra, so we turn off the laser, and which we make a comparison. So in spectra graph, so we go in the spectra, we delete all the spectra, and we load this new spectra. So we have open slit. Allora, lead, ecco, okay, lead tin open slit. So there it is. Raman counts, okay, there it is. Then let's see what happens when we close the slit. Okay, so this is the important concept. So let's magnify maybe in this area. To get the idea. Okay, so in particular you see for this peak over here, let's go into here, multi-cursor, so okay, there it is, so I can move. So for example, this peak here, so the presence of the slit open or closed doesn't change much, because we have just one peak. Here it's more thin, here is more larger in the open slit, but the peak is there, the position is there, so we know there is the standard peak of lead tin yellow. The thing is different when we look over here for this peak. So when we have peaks that are very close, so like in this case, okay, so if we have a lot of resolution, we can distinguish them, so they start to look separate. Otherwise, they would be very close. But still, I mean, in this case, I can tell immediately that there are two peaks together. They are just so close that they kind of merge together. Okay, and then we have the main peak. You see, the idea is that the main peak start to be very thin when we have a much higher resolution. Okay, so lead thin yellow, one type. So this one is a good example of playing a little bit with the slit, finding this average value. So generally I recommend to start with 2x, so this value at least with the knob 2x, because it's an intermediate value. Actually, let's see it. We didn't load it yet. So we have lead thin, where is 2x over here? Okay, let's load it. Okay, so it's this orange color. Okay, so let's make it another color because it's a little. So 2x, let's make it different color. Let's make a nice green, so it's much more different. Okay, and make it more more thick, so we can tell it immediately. Okay, there it is. So basically from here we see that using this 2x we have better definition of these two separate peaks. So that's why I say it's a good compromise, because anyway we have more signal, so it's good to have immediately the spectrum with less acquisition time. But also the peaks are well defined. And then if we want to have much better defined spectra, just close the slit all the way down and you'll get the better resolution. Okay, thank you for listening.